what I want to just close today's lecture with is some examples of tensors that become very useful as you go forward. The first is what we call a dyad. And sometimes it's a challenge because it looks a lot like a dot product, but a dot product is a scalar. So keep in mind, u dot v is ui vi, and that's a scalar. How do you know that's a scalar? No, how many indexes should a scalar have? 0. Why is this 0 indices? You sum over the i's, and when you're done summing over the i's, there's no index left. So that is a scalar. That's not a dyad. The dyad does not equal that. The dyad equals ui vj, which will sometimes be written as uv, just next to each other. It's a product. I take the ith component of u, and multiply it by the jth component of v. And how many numbers will I get if I'm in 3 dimensions?
3. Wait, 1. Sorry.
If I go through all the components, how many numbers do I get in 3 dimensions? 9. I do it for all the i's, I do it for all the j's, and I'm going to get 1, 1, 1, 2, 1, 3, 2, 2, 2, 1, 2, 3, 3, 3, 3, 1, 3, 2. So this has 9 elements. This represents 9 different numbers. And it's the tensor Tij equal to ui vj. That's in component form, which I then can write as a matrix. The cool thing is, I can quickly prove to you it is a tensor. Well, what's the definition of a tensor?
T prime ij equals a Tij a transpose.
Well, let's keep it. Let's keep it this way.
Oh my goodness.
Everything on that side.
Okay.
Right. It's a lot easier when you're doing index notation. It's a lot easier to work with AMJ, not the transpose, because then you're always working with A itself. And it just, I could have put IJ here and put IL, JM, and LM here. Your letters don't matter. I just didn't want to confuse myself, so I matched my notes. Actually, I will confuse myself because my notes used K, but what the heck. So now I can just look at this, right, and plug it in. This equals ALI, AMJ, UI, VJ. Right, I just plugged in for Tij. And now what do you think I'm going to do? I'm not going to, what do I know about multiplication?
It commutes.
It commutes, and I can do it in any order, right? It's associative as well.
Yes.
So what am I going to put next to what? So I'll group that, and I'll group that. And now what do I have? What is ALI times UI by definition?
Vector.
Which vector?
The L components, the sum of all the i's.
But if I take my transformation matrix times my vector, what have I just done to it? I've changed its basis. So now what do I call this thing? U prime I. I just changed its basis. It's U prime I. And what is this thing? V prime J. Is that? Oh, actually, no, we lied. It's not I and J. When I sum over the I, what component do I get?
L.
L. And when I sum over the J, what component do I get?
M.
M. And so what do I see? This is exactly TLM prime by definition. This is not circular. This is an actual proof that a dyad is always a tensor. By definition, by construction, I've constructed an object that transforms under the definition of how a tensor should transform. Therefore, it is a tensor. So a dyad is always a rank 2 tensor. And this is another example, because you're going to have to manipulate some of these things yourself in the homework. There are two other critical tensors. Oh, I should just say, one place this gets used a lot is with the grad operator. So this object, if I write it as grad u, both with the vector sign, that's a tensor. That's 9 elements, grad sub I u sub j, where grad sub I is d by dx, d by dy, and d by dz, 1, 2, 3. So that's a notational thing we use a lot that helps. Grad is a vector, d by dx, d by dy, d by z. We can label them by 1, 2, 3, and we can use indexes to keep track of it. The other two pieces in our 2 minutes, we get 1 minute for each, is the Kronecker delta, delta ij, which is a rank 2 tensor. It's 1 if I equals j, and it's 0 if I is not equal to j. This is basically the identity. I'll make my delta a little nicer. There. That's the easy one to use. The harder one that you're going to practice with on the homework is epsilon ijk. This is either 0, 1, or minus 1. It's 0 if any two indices are the same. It's 1 when they're equal to 1, 2, 3, or any symmetric perturbation. And it's minus 1 for any anti-symmetric perturbation. So what does that mean? That means epsilon 1, 2, 3 is equal to 1, but epsilon 2, 1, 3 is equal to minus 1. Because I flipped the 1 and the 2, I can't do that by just permuting these around cyclically. So another word for the symmetric here would be cyclic. Okay. So what would be epsilon 2, 3, 1? Plus or minus 1?
Plus.
Plus 1, because I've just rotated them through. And the reason we introduce epsilon ijk, and this is the final piece I'll use, is it really gives us the cross product. The ith component of a cross product can be written that way. And that's the last piece I'll leave you with, because I sum over j and k. But notice, for any component of the cross product, say the x component where I equals 1, what are the only values j and k can have? If this is already 1, what can j and k be?
2 and 3.
2 and 3 only. They can't be both 2 or both 3. So only 2 terms survive in my cross product, which you know is true. Right? The x component of the cross product is what? ay bz plus or minus? Minus bz, minus az by. And notice when I flip the 2 and the 3, I pick up a minus sign. So this is exactly the cross product. We're going to do an example with tensors to start tomorrow. That'll help with this. But this gets you all the main ideas for tensors. And we're good.